just you. All right, yeah, I'm recording now, so let's. All right, so basically you have my videos, right? Which is good. So tomorrow is a maybe because what I mean by maybe, I maybe not want to be in the classroom. And then if I'm not, I don't think we necessarily have to meet remote since we have WhatsApp. But if I show up, I show up. You're all going to be in the room. You can remote in however you want. And then I could even make a Blackboard session. But anyway, and then you can go over stuff. But anyway, 2.1 is due formally today. Hannah, you need to email to me so anybody doesn't have it with you. 2.2 is essentially due, but I do like being able to go over questions since I haven't really covered it in class. So one question you said 6.
6C especially.
6C is an even, and I don't do evens, you do. But I can answer a general question on it. What everybody else get, that'd be my first question. We got a right-handed derivative and left-handed derivative and differentiability versus continuity. Did everybody watch all of my videos? Not an option. What are you confused about? Like where they're at? Confused on what? Continuity versus differentiability? Why are you throwing stuff at me?
I think around this paper though.
Oh, right. You got 2.1. 2.1, you're good on that, right? So handles it. What's your question on? What's your question on 60? Yeah, all these. Scan it, you could then bring the original. All right. So anyway, sorry. I know you can't see right now. Here, we'll put you that way. Say hi to your classmates. Can you see your classmates? Okay. Let's see. Left-handed and right-handed derivative. That's what you want to know. Okay. That's fine. So basically, yeah. Let me just write that up here. Then we'll go back. Okay. So just like we have right and left-handed continuity, the point. What was the difference between continuity and right-handed continuity? Yeah, the bullet point number 2 was the limit as x approaches a from the right. It was the right-handed limit, correct? So for differentiability, so remember f prime at x sub 1, if I have a particular x sub 1, is the limit as delta x approaches 0 from both sides, right? Of f of x sub 1 plus delta x minus f of x sub 1 all over delta x. And as we mentioned yesterday, I don't really care if it's an x sub 1 for a particular x or you just call that x for any x. It doesn't really matter, right? The delta x is its own variable. If I want the right-handed derivative, that's the instantaneous rate of change as we approach from the right. That would be f prime from the right. So I put the little plus sign in the subscript since f prime is in the superscript. The prime is in the superscript. So the right-handed derivative at x sub 1 is nothing more than the limit as delta x approaches 0 from the right of the same difference quotient. The difference is I'm only going to approach from the right. So if you remember, I drew my picture on the right board over there for the derivative, which is the slope of the secant line as the secant line gets closer and closer and closer to that point for both sides, but we're only approaching from the right side. So you're only making secant lines from the right and getting closer and converging on that. Now, why do we want something like this? Because we might have this. We might have the square root of x. F of x equals square root of x. What's the domain of f? including 0, which I could write r plus including 0 for shorthand, or including 0 to infinity. So is it possible to find out what, first of all, if I say what's f prime at 0, what is it? Well, this actually does not exist, okay? And the reason is because if I try to do this up here, this top one, so I'm taking the limit as delta x approaches 0 from both sides, but this has no approach from the left. It's not defined for left. So in other words, the left-handed derivative wouldn't exist. You cannot approach this function from the left side at 0, right? Okay, so there's a couple of reasons why this doesn't exist at 0. One of them is if I try to balance a tangent line, I can do that anywhere to the right of 0. I could balance a tangent line, correct? And so if I'm out here at, say, x equals 4, I would have a tangent line that's fairly flat, but I could balance that tangent line against the curve. When I get to 0, what happens? I get, if I'm at 1, my tangent line would be steeper, correct? If I get to 0, what happens to my tangent line? It kind of spins around. So if you have something that spins around and sitting on a point, it's spinning around. I kind of think of when you play Twister, you got to click that little arrow and it spins around. If it's going to do that to you, there's no tangent line that balances on that. So for sharp points, like at the origin for absolute value of x, or for something like this at 0, which has a stop at 0, you're going to have a tangent line that doesn't balance. So sharp points, flat points, the tangent line doesn't balance, which the tangent slope of the tangent line is the derivative, right? So this is also known as the slope of the tangent line at that particular point. So in this case, because of the concept that I can't balance the tangent line at the origin, this doesn't exist. But I can also prove that it doesn't exist by looking at the right-handed derivative and the left-handed derivative. Okay, so blue, let's see, we have right-hand derivative red, left-hand derivative blue, just like right-handed continuity and left-handed continuity, correct? I'm going to have right-handed derivative in red, and then of course the left-handed derivative that would be f prime from the left, so a little subscript of the minus sign, at x of 1. The only difference with this is it's the limit as delta x approaches 0 from below, though, from the left. So that's the left-handed derivative of the same difference quotient. The difference quotient doesn't change. I'm going to go back and give the alternate definition as well. How else could we say, let's go ahead and use the alternate definition. We were letting x approach x1, right? So the alternate definition of this says equivalent to the limit as x approaches x1. But if it's the right-handed derivative, how am I approaching x1? From which side? Right. How do I indicate that? A little plus sign there. x1 from the right. Can you still see that, Hannah? This was f of x, the difference quotient, the alternative definition, f of x minus f of x1 all over x minus x1, right? So this one I could also have the alternate definition. Instead of delta x approaching 0 from the left, I could have, this is equivalent to the limit as x approaches x1 from the left, so a minus sign in the superscript, right? So same thing, f of x minus f of x1 all over x minus x1. All right, so anyway, let's go back to the square root. And so now the question is, so we've got left and right-handed derivative. By the way, I'll give you a little hint. The continuity we had, it's continuous at a point. We had a theorem, a proven fact. We had continuity at a point if and only if it was left-handed continuous and right-handed continuous at that point. Correct? Remember that? So it's going to be the same thing with differentiability. Our function is going to be differentiable at a point. In other words, the slope of the tangent line would exist at that point if and only if it has right-handed differentiability and left-handed differentiability at that point.
Does it have to equal?
And yes, but it's got, yes, have to be equal. Yeah. Which absolute value, but in this case, there is no left-handed derivative at 0, so there's no derivative at 0. But the absolute value one, we should look at that one. Okay. Anyway, so let's look at one that we do have though, the right-handed derivative. Now, which version do you want me to use? The basic one, the first one I wrote? The delta x ones? Do that. Okay, so the right-handed derivative, so that the f prime from the right at what? 0, right? Okay. This is going to be the limit as delta x approaches 0 from the right. Delta x approaches 0 from the right of, okay, what's f of x1? x1 is 0, right? So it's f of delta x. So what is that? Square root of delta x, correct? Right? x1 is 0. Oh, this is 0 here. So minus f of 0 would be minus the square root of 0. Do you want me to write that in here? Minus the square root of 0 all over delta x. Everybody okay with that? Anyway, so it just becomes the limit as delta x approaches 0 in a positive from the right or in a positive way. Square root of delta x over delta x. Well, what's that? That's I'm doing wrong here. No, well, I'm not doing anything wrong. Anyway, but if you cancel that out, what do you get? Like, how do you do that? It's 0 over 0, but what is it? Right? But I can manipulate it. One way would be to rationalize the numerator, take it times the square root of x over the square root of x. And then on top, you got delta x over delta x. Or I could factor the bottom as square root of delta x times square root of delta x. What do you prefer? First one, right side, so take top times square root of delta x, bottom times square root of delta x, which is okay because it doesn't equal 0, right? Same thing over same thing. Anyway, what happens is that ends up being delta x, right? That cancels with this delta x, and I get a 1 on top. So it's 1 over the square root of delta x. What's that equal? Limit as delta x approaches 0. So I'm going to come back here. So this equals limit as delta x approaches 0 in a positive way of 1 over the square root of delta x. What does that equal? Thank you. Positive infinity. This is why we did all that crap in chapter 1, right? This is an infinite limit. Because if I plug in, I get 1 over 0, which is undefined, but how are you approaching 0? We need to know. I have a fixed positive number on top. On bottom, I have something from 0 in a positive way. So it's exploding up, right? So this ends up equaling positive infinity. If you know this, that makes sense, because I'm going to get steeper and steeper and steeper as I get close to 0 from the right, for my tangent line, right? Okay, well, what if I did the left-handed derivative? What's the difference? I have the left-handed derivative of this same thing, even if I'm using that formula. I have the limit as delta x approaches 0 from the left of the square root of delta x over delta x. What's the problem? Why? Because you have a tiny negative number under a radical, under a square root. Can't do it. So this does not exist. So the left-handed derivative doesn't exist. The right-handed derivative exists and equals positive infinity. Therefore, f prime of 0 does not exist. Okay. Once again, so the concept there is, if it's going to spin or not balance, then the derivative isn't going to exist. Do you want me to see? Okay, so you follow the square root? example. Do you want me to do the alternate definition? You gotta let me know if you can't see where I'm writing. You look so tiny on the computer. Anyway. All right. Let's do this. Let's do this one. So what's x1? 0? Sorry, I shouldn't have circled that in red and blue. Should have been red. Anyway, this one's 0, right? So what do I got? I'm just going to go right here. This would be the limit as x approaches 0 from the right. Okay? Of f of x is just the square root of x minus f of 0 is the square root of 0. Okay? All over x minus 0. Okay? So it ends up being the same deal. It's the square root of x over x, which is 1 over the square root of x. So it's the limit as x approaches 0 from the right of 1 over the square root of x, which is 1 over the square root of a positive 0, which is a positive 0, which explodes to positive infinity. Okay? I don't care which one you use. They're equivalent. So if you have one you like better, if I didn't tell you which way to do it, which format of the definition to use, pick your choice. Okay? Once again, when we get into section 2, 3, and later, we're going to have some other theorems that we can use as well to come up with what the derivative would be in different places, but we are going to need to look at points. Once again, if I have the left-handed derivative, what's the problem? I got 1 over the square root of a negative 0, right? For the left-handed derivative, I end up with 1 over the square root of a negative 0, which does not exist. Correct? And I'm skipping some steps in there, but that's why it's a problem. All right? So let's just, can I erase the right side of the board now? And you can see this all right over here, Hannah? So let's go absolute values. Basically, what's the derivative? Well, what's the right-handed derivative? Let's do that in blue. No, red for right. Sorry. Which one do you want to use? The limit. Let's do the x to x1. So let's go the limit as x approaches 0 from the right of f of x, which is absolute value of x, minus f of 0, which is absolute value of 0, which is just 0, right? All over x minus 0. Okay, so what's that equal? Limit as x approaches 0 from the right of the absolute value of x over x, which I don't want, I need to rewrite the absolute value of x without the absolute value sign. Simple. Well, no. What is the absolute value of x if x is a tiny positive number? It's just x, right? So this is equivalent to the limit as x approaches 0 from the right of x over x, since x is greater than 0, right? It's positive. You just drop the symbol. With 1, and the limit of a constant is a constant, right? K equals k, is that how we were doing that one? Limit of the constant is a constant, so that equals 1. Now, does that make sense? Let's just look at our graph. Can you still see that? Do you see my 1? Is that about the end of it? Okay. Well, let me just draw the graph smaller here. We all know it's a V, right? But anyway, straight lines, right? This is straight lines. This is y equals x on the right, y equals minus x on the left. What is the slope of the tangent line? If I'm over at 5, what's the slope of the tangent line for y equals x? Same as the slope of the line. Is what? It's y equals x. What's the slope? 1. So what would the derivative of this function be for x equals 5? 1, because it's the slope of the tangent line, which is the same as the slope of the line, because it's the same there. But guess what? You go all the way back to zero as you get closer and closer and closer to zero. From the right, you always have a slope of 1. Correct? All right. What do you think is going to be from the left? I shouldn't even have to do that. But what's the left-handed derivative at x equals 0? -1. If I said, what's the derivative at -5, you're going to say it's -1, so that's the slope of the line. Slope of the tangent line is the same as the slope of the line, because it's the same, right? And as I get closer and closer and closer, I still have a slope of -1. Slope of the tangent line on the left side is going to equal -1, which is actually the derivative at any point over there. If x1 is less than 0, f prime at x1 equals -1, right? Now I'm going to go ahead, since some of you like the other way to do it, let's just do it the other way. Let's say that you've been doing it this way because you didn't know any better. You didn't realize that looks pretty when you do it right. So let's just say you took the limit as delta x approaches 0 from the left. What is it? It's f of x1 plus delta x. x1 is 0. So it's f of delta x, which is the absolute value of delta x, right? Minus f of x1, which is the absolute value of 0, all over delta x. Agree? Which is, you got to remember, delta x is its own variable. It's like a z, or actually it's like an h, right? It's designed to be a tiny number. Okay? Anyway, so if I have that, now what I got? So this equals limit as delta x approaches 0 from the left of absolute value of delta x over delta x. I need to figure out what that is. So how can I rewrite it without the absolute value symbol? It's minus delta x, because delta x is a negative number. What's the absolute value of a negative number? The opposite of that negative number. Because we take a negative number and make it positive, right? So writing this without the absolute value symbols is going to be the limit as delta x approaches 0 from the left of minus delta x over delta x, correct? Why? Since delta x is less than 0. It's a tiny negative number because I'm approaching 0 from the left. Okay. So this is without the absolute values, and of course that's going to cancel out to what? -1 over 1. The limit of the constant is constant, so that's -1. Okay. So this comes back to Isaac's point. Well, don't they have to be equal? But yeah. So like over here, the left one didn't exist. So we don't even need to get that far. But here, the right-handed derivative at 0 exists, and it equals 1. The left-handed derivative at 0 exists, and it equals -1. However, they're not equal. Therefore, f prime at 0 does not exist. Since the left-handed derivative does not equal the right-handed derivative. If one of them doesn't exist, it's not going to exist. If they both exist and they're not equal to each other, it's not going to exist. Make sense? By the way, let's go back to this. If I just use my black marker, and I like to use dashed lines when I don't have different colors for my tangent line. If you try to balance a tangent line on that sharp point, what happens? Well, it could be the x-axis, it could be like that, right? I mean, it's going to spin. It's going to spin on that point. If you don't believe me, turn it upside down, then try and balance a line on top of that sharp point. It's going to teeter-totter, isn't it? Potentially spin around if there's no ground to hit the one side of the teeter-totter. Right? So, okay. Does that help? Do you think that helps you for number 6? Okay, because is it one that, yeah, if you have awkwardness with the first format of the definition with the delta x, try it the other way. There's some really nice outputs when you try it the other way with the alternate definition.
You can use your equation thing?
Yes, yes. Okay. And in fact, up here, just for the this definition, the alternate definition, this is equivalent to the limit as x approaches x1 from both sides If I don't dictate a side, it's both sides, right? So f of x minus f of x1 all over x minus x1. And by the way, this is the only thing I don't like about this book besides it's old and rickety, right? But it's free, and your parents would have had to pay for like $200 for a book and code and then online stuff that we're using for free at Khan. So they didn't have to do that, so that's good, right? Saved you $200. But to take care of those books. But anyway, in chapter 1, we weren't calling it x approaches x1. What were we calling it? X approaches a, right? So I'm going to use a different color. We'll use green with envy, because if I wrote a book, I'd say, hey, this is the limit f prime at a, which is the slope of the tangent line when x equals a on a function, right? It's going to be f prime at a. It's going to be the limit as x approaches a from both sides of f of x minus f of a all over x minus a. So it's still a difference quotient there, right? Still a difference quotient, but they somehow, for some reason, change it over to x1 being a particular point. I will tell you, yet again, I'll use a different color. I use purple because obviously I'm going to have some work to do to clean up the board. Here's another thing. I can have another point to the right or left of x1 called x2. Well, how else could we do it? Well, we could say the limit is x2 approaches x1 from either side, from both sides, right? So x2 could be to the right or it could be to the left. This would be f of x2 minus f of x1 all over x2 minus x1, which the bottom is equivalent to what? Delta x, right? Change in your x's. What's the top equivalent to? Well, the change in your what? Heights. Yeah, your y's. No, absolutely, your y's. This is equivalent to delta y. What's delta y over delta x? Slope of what line between those 2 points? x1 f of x1 and x2 f of x2. No, not tangent. Secant line. Is that what you said? I wasn't listening. Over the secant line, right? And what are we doing? We're letting the limit as x2 approaches x1 or as delta x approaches 0, letting that secant line get closer and closer and closer and closer to the tangent line. And that's where we come up with the derivative. Amazing stuff. This is the theory of calculus. So if you're following me today, you should feel good that, hey, I really understand the foundations of what calculus is trying to do to come up with an instantaneous rate of change of a curve at a point. Okay, that's calculus. And we get some easy stuff that develops from this that ends up being really nice starting in 2.3. But this is the theory. This is what your previous calculus teachers have glazed over because they know there's an easy way. Well, if everything's easy, everything is easy if you know what you're doing. This is knowing what you're doing. At Iowa State, somebody said they went to Iowa State when I thought they were going to UNI, and we say, But at Iowa State, I had former Calc 1 students taking Calc 2, and none of the other students in the 300 knew what this was. Like, didn't understand what a derivative was. They're just like, well, you just take it. Derivative of x squared is 2x. They knew how to do it. They didn't know what it meant. And my student, this is decades ago, back when I was a younger version of myself, they're like, it's the instantaneous rate of change of curve, it's the slope of the tangent line, right? I mean, they're able to explain that. They're like, all these other students from all these other towns, like, in states had no idea what they're talking about. That's what you get because you get me. And this will help you when we get to the easy stuff, right? But it is important as well. All right. So if there are other questions on 2-2, I'd like you to have 2-2 as done as you can for tomorrow. For the evens. If there's issues along the way, use the WhatsApp. If you can't help each other out, make sure that I'm helping you or seeing what you're stuck on. Because I'm okay with that, because I'm not going through every detail of the videos. If you haven't watched all my videos, you need to watch my videos. Okay, 2. Where are you going? Bell hadn't rung yet.
Didn't know if you can pencil my phone.
Oh. Was it cleaner in here today on the food at the desk?
Not really, I think dirtier. Because like those two.
I can ask. I can ask Logan. I did say something. They said they were gonna remind people to be respectful and clean stuff up. Any questions? Okay. What, Elvis lives? Oh, yeah, right. No, I don't want to mess with my stuff. Okay. I'm gonna stop recording since I'm moving you around.